Last episode, LoRA cut the training cost. We fine tuned a model by touching barely a quarter of 1% of its weights. But here's the thing, once you've got that fine tuned model, you still have to serve it. And serving is its own bill. Every time someone sends a request, the full set of weights has to sit in GPU memory and run a forward pass. Quantization is the trick that cuts the serving cost of that very same model. Same weights, same accuracy, just stored in fewer bits. Today we load one model 3 ways, full precision 8-bit and 4-bit, and we watch the memory footprint and the latency drop right in front of us. So what actually is quantization? A model's weights are just numbers, billions of them, and by default each one is stored in 16-bit floating point FP16. That's 2 bytes per weight. Quantization asks a simple question: do we really need all 16 bits to capture each number well enough? Turns out, often we don't. We can squeeze each weight into 8 bits or even 4 with a clever scaling scheme, and the model still answers almost identically. Fewer bits per weight means a smaller model in memory. Here's the intuition with one number. Say a weight is 0.3174 in FP16, lots of precision. In 8-bit, bits and bytes maps the whole range of weights onto just 256 buckets, so that weight becomes the nearest bucket. Maybe it rounds to 0.31. In 4-bit, you only get 16 buckets, so it lands on something coarser like 0.3. Each step throws away a little precision, but saves a lot of space. The magic is that neural networks are remarkably tolerant of this rounding. Why does anyone care? Memory. A 7 billion parameter model in FP16 needs about 13.5 gigabytes just to hold the weights. That won't fit on a lot of consumer GPUs. Drop to 8-bit and it's roughly halved. Drop to 4-bit and you're down near a quarter of the original. Suddenly, a model that needed a data center card fits on a gaming GPU. That's the whole reason 4-bit quantization exploded. It put big models in everyone's hands. In Hugging Face, this is almost free to use. You build a tiny config object, a bits and bytes config, that says load this in 4-bit, and you hand it to from pre-trained. Transformers and bits and bytes do the rest. They download the FP16 weights and quantize them on the way into GPU memory. You don't retrain, you don't convert files by hand. One config, one argument. There's a nice detail in the 4-bit path called NF4, normal float 4. Instead of spacing those 16 buckets evenly, NF4 spaces them to match how weights are actually distributed, which is bell-shaped and clustered near 0. So you spend your precious 16 buckets where the weights actually live. That's why 4-bit NF4 holds accuracy so much better than a naive 4-bit rounding would. We turn it on with one flag. Now what about speed? You might expect smaller to always mean faster, but it's subtler. Quantization mainly saves memory, not necessarily compute. The matrix multiplies still happen. What you gain on latency comes from moving fewer bytes around, less data to read from memory each step. In practice, that nets a modest latency win, a few milliseconds, on top of the big memory savings. So the headline is huge on size, gentle on speed. That sets up exactly what we measure. We load the same model 3 times, FP16 8-bit, 4-bit, and for each we record 2 numbers, how many gigabytes it occupies on the GPU and how many milliseconds one generation step takes. 3 loads, 2 measurements each, 6 bars. Let's go see them in code. One file, Zo9 quantization.py, 4 short pages. Page 1 sets up imports and a tiny helper that measures the model. Page 2 loads the model 3 ways. Page 3 runs the measurements and collects the numbers. Page 4 prints the comparison line. By the end, we'll have the exact summary you saw up top. Page 1. We import torch, time for the latency clock, and 3 things from transformers: auto tokenizer, auto model for causal LM, and bits and bytes config, the object that describes how to quantize. We pin a model ID, a 7 billion parameter base, and a short prompt to generate from. Then a helper measure that takes a loaded model. It reads the GPU memory the model occupies, times a single short generation, and returns the gigabytes and milliseconds. That helper is the whole measurement story in one place. Page 2 is the heart of it, loading 3 ways. First, full precision from pre-trained with torch d-type Chaborok torch dot float 16 straight onto the GPU. Second, 8-bit, we build a bits and bytes config, load in 8 bits true, and pass it as quantization config. Third, 4-bit, another config, this time load in 4 bits true with BNB 4-bit quant type NF4. That's the NF4 flag we talked about. And a compute D-type of float 16. 3 loads, same tokenizer, same model, 3 precisions. Page 3 runs the experiment. We call our measure helper on each of the 3 models and stash the results in a small dictionary keyed by precision name. FP16 comes back around 13.5 gigs and 42 milliseconds, 8-bit around 7.2 gigs and 38 milliseconds, 4-bit around 3.9 gigs and 31 milliseconds. The numbers are the payoff. Memory falls off a cliff, latency eases down. Page 4 just formats. We pull the 6 numbers out of the dictionary and print one clean comparison line. Each precision with its gigabytes and its milliseconds, pipe separated. And there it is, the same fine-tuned model, now small enough and fast enough to actually deploy. Memory cut to under a third, latency trimmed, accuracy essentially intact. The model is small and fast, so next time to make it actually right, we call generate and watch it produce language one token at a time.